all of you. Welcome to the 23rd lecture on the course on analysis and modeling in chemical engineering. We have been discussing about evaporators. We started with single effect evaporator, and then in the previous class we were doing multiple effect evaporator, both forward feed and reverse feed. We did the mass and energy balances and heat exchange equations for the forward feed case for a triple effect evaporator. So, in this class I am going to do the same thing for a triple effect evaporator, and then we can do some problems on the evaporators. So, just to recap, we were doing for the forward feed, and this was the solution scheme that we finally got at. We had assumed here that the heat transfer coefficient of the three effects are the same, and that is equal to U, and the heat transfer area is also same for all the effects. This is not generally true, but this was assumed for simplicity. And then what we have also done is we eliminated the vapor flow rates, vapor mass flow rates, using the overall mass balance, and then we were left with basically 6 equations concerning the energy balance and the heat exchange equations. When we also separated the solute balance equations, the reason being that the solute mass fractions are appearing only in these equations, not the first 6 equations. And then for a given choice of unknowns, we had a scheme where we said that the first 6 equations we will solve using, and we get these 6 unknowns, and the solute mass fractions can be gotten from the solute balance equations. And of course, keep in mind that the latent heats, the pressures and the heat capacities has to come from property relations, and I am not discussing that, but keep in mind that those are highly nonlinear equations in general, and therefore these equations appear to be simple, but in reality it is going to be computationally expensive to solve, and we will discuss how to solve it numerically later. But just to give you an impression that this is not very straightforward to solve, because the latent heats, the heat capacities, these can be very non-trivial, right? In this case, we assume the heat capacity to be constant, but the latent heat at least depends on the temperature, right? So, in this case, lambda s is some function of Ts, lambda 1 is some function of T1, lambda 2 is some function of T2, and lambda 3 is some function of T3, and these are going to be non-trivial functions, and the equations are therefore not linear, they are highly nonlinear equations. Okay, so let us now do it for the reverse feed triple effect evaporator, and just how I explained the reverse feed in the previous class. The feed enters the last effect or the coldest effect. As we said, the pressures are decreasing along the effect, and the temperatures are also decreasing along the effect, and the feed is entering the last effect. This can be helpful if the feed is cold, or if my final product is viscous, the liquid is viscous. So, in that case, higher temperatures will lower the viscosity, and they will be easier to flow out from here, right. So, we will do it for the reverse feed. The feed enters the third effect, but the fresh steam enters the first effect at temperature Ts and Ps. And let us do it for a general case where we have different heat transfer coefficients and heat transfer area, but of course we can make the same approximation later that the heat transfer areas are same and heat transfer coefficients are also same. But let us do it for a general case. So, again we still have the same notation P1 T1, P2 T2, P3 T3. V1 V2 V3 is pretty much same as earlier, they are going in the same directions, but now what has changed is earlier in the forward feed case, the liquid product of the first effect was going to the second effect. So, this was going here, but I am not doing that. Now, the liquid product of the third effect is entering the second effect. So, L3 comes here, and liquid product of the second effect enters the first effect. So, L2 comes here and L1 comes there. Some kind of a counter current operation. The vapor is going in this direction and liquid is going in opposite direction, right. And of course, we have discussed the advantages for these cases. So, let us now do the overall mass balance for the three cases. So for the, now we can start from the backwards because the feed enters the last effect. So F enters here and the streams going out are L3 and V3. So this vapor that is coming in, keep in mind it is a heat exchange media, so it is not mixing with the liquid in third effect. So F is basically distributed into the liquid and vapor. So F is equal to L3 plus V3. Similarly, for the second effect, L3 is entering and what is leaving out is L2 and V2. That's my second equation. And for the first effect, L2 is entering and what is leaving out is L1 and V1, and that is my third equation. The solute mass balance is pretty much unchanged, right? The way we have written it can be opposite of that, but in the end the equation is not changing because Fxf, that is the first where the feed enters the last effect, this is the amount of solute in the feed, that is equal to whatever is going out in the liquid leaving the third effect, and there is of course no solute in the vapor. So this becomes L3 into XL3. Now for second effect, what is entering is L3 XL3 and what is leaving is L2 XL2, and for the first one, what is entering is L2 XL2 and what is leaving is L1 XL1. And if I do that, I will get pretty much the same equation that we had earlier. The solute mass balance is pretty much unchanged. Now the energy balance will of course change. Let us start with the last effect again. So the sensible heat change of the feed in the third effect is simply now FCP Tf minus T3. Tf is the entering temperature and T3 is the temperature of the effect and also what is going out of here. So this is my sensible heat change. The vapor V2 is now the heating media. So V2 lambda 2 is the latent heat that we get from the condensation of that V2, which gets condensed here. That is my heating media. And the vapor that is going out, the third effect, is now carrying this energy, that is the enthalpy of the vapor going out, right? And of course, I have done the same kind of math which I had done earlier. Now, similarly, for the second effect, what is entering is my L3 at temperature T3 because it's coming from the third effect. The sensible heat change will be now L3 Cp T3 minus T2 because T2 is temperature of second effect, and the heating media in this case is V1, which is coming at temperature T1. So V1 lambda 1 is the amount of heat supplied by this vapor that is condensing here, right? And the vapor that is leaving the second effect is V2, which is at temperature T2 and has latent heat lambda 2. And now we can do for the first effect, what is entering is L2 at temperature T2 and the operating temperature of first effect is T1. So the sensible heat change is L2 Cp T2 minus T1. And now for the first effect, the fresh steam is the heating medium. So we have S lambda S, that is the heat supplied by the steam, it is condensing inside and going out here as a condensate, and the vapor leaving is carrying this enthalpy V1 lambda 1, right. So we have written the energy balance for the reverse feed, which is much different from what we had for the forward feed. Now we can also write the heat exchange equation, which are pretty much unchanged. The reason being that the vapor is still flowing in the same direction as it was flowing for the forward feed case, right. In the first effect, the heat supplied is S lambda S by the steam, that is equal to UA delta T. This is in this case U1 A1 into delta T, that is Ts minus T1 in this case. For the second effect, the vapor is being used to heat up. So vapor is coming with a temperature of T1, so latent heat of from lambda 1 at temperature T1, that is equal to UA delta T. So we have U2 A2 in this case, and delta T is T1 of the vapor that is coming in and T2 of the operating temperature of the effect, so T1 minus T2. And similarly for the last one, we have V2 as the heating medium. So V2 lambda 2 is the energy that we gain by condensing it. It is at temperature T2, of course, and it is equal to U and delta T again. So in this case U3A3, and delta T is the temperature of the vapor coming in, T2, minus the temperature operating in the effect, that is T3, that is T2 minus T3. So if I combine all of that, these are a set of equations that we get here. So again we have three mass balance equations, the overall mass balance equation, three solute balance equations, three energy balance equations, and three exchange equations. And of course, we have all the property relations, which I am not discussing again, but they will come from some property data like a steam table. How we can solve it? I can again do the same thing. I can eliminate the vapor flow rates from the overall mass balance equations. So, I can replace V1 by L2 minus L1 from the first equation, V2 by L3 minus L2 by second equation, and V3 by F minus L3 from the third equation. So, henceforth, I am going to pretty much drop the first three equations because I used it to eliminate V1, V2, V3, and I will only solve the remaining equations. In here, I will all the places where we have V1, V2 and V3, I am going to replace with the expressions that we have got here. Okay. So, if I do that, and if I also again assume that the heat transfer coefficients are the same and the area of the effect are the same, in that case again we have 6 equations characterizing the system, which are energy balance and heat exchange equations, and I am not counting or keeping separate the equation of solute mass balance, again because the mass fractions are only appearing in these 3 equations toward here, right. So, the mass fractions do not appear in the first 6 equations. So, I will anyway do it separate, right. So, again we can make a choice of given variables, right, and the choice of unknowns, right, and I can pretty much follow the same logic. The first 6 equations will give you these 6 variables and the 3 mass fractions will come from here, right. Keep in mind here that when I was doing it for the forward feed, it was slightly different choice of unknowns. I have chosen the unknowns as S, L1, L2, T1, T2, A. The first 6 unknowns were different when we are doing this forward feed, but now we are making a different choice, forward feed, but now we are making a different choice. And the reason I am doing that is because this becomes convenient, and I will discuss later like why it is convenient and what advantage do I get by checking this kind of unknowns. And the advantage in this case must be computational advantage. Of course, there is some intuition that we can use here. In this case, let us say T1 may be known to us for whatever reason, that can be my intuition. But then in most cases, we will pretty much follow whatever makes our job easier, right. So, if I am designing an evaporator, I can make sure that whatever unknowns I choose gives me a set of equations or the solution scheme that is easier to solve rather than making it more difficult, right. Again, I emphasize here that this lambdas are highly nonlinear and it is not, although equations appear to be simple, they can be quite complicated. Okay. Just to demonstrate the advantage that we get if I am using multiple effect as opposed to a single effect, let me simplify these equations somewhat and assume that the sensible heat changes are negligible, just to demonstrate the idea that what advantage we get from the multiple effects, right. So, I will write the equation for the forward feed and then we will assume that the sensible heat changes are negligible, right. So, the equations that we had got was something like this for the forward feed triple effect, FCP Tf minus T1 plus S lambda S is equal to F minus L1 lambda 1, where I eliminated V1 with F minus L1. For second effect, I had L1 Cp T1 minus T2 plus F minus L1 lambda 1 is equal to my L1 minus L2 lambda 2. And then for the third effect, we had L2 Cp T2 minus T3 plus L1 minus L2 lambda 2 is equal to L2 minus L3 lambda 3, right? And then finally, we have three heat exchange equations, which are S lambda S is equal to UA Ts minus T1 and F minus L1 lambda 1 is equal to UA T1 minus T2, and then L1 minus L2 lambda 2 is equal to UA T2 minus T3. So, if I drop the sensible heat term, or if I assume that Cp is negligible, or the sensible heat, that is Cp delta T, is much less than the latent heat, in that case I can drop the first terms from these three equations. So, this will go away, this will go away, and this will go away, right. Now, going further, let me also assume, just for the sake of argument, although it is far from truth, that the latent heat is also constant. It is not changing with temperature, right, just to demonstrate bring the point home of what advantage do I get if I use this multiple effect evaporator. But before we do that, let us see one thing here, that now the first three equations are actually can be combined together. So, this is equal to this, which is also equal to this, and which is also equal to this, right, because the same term appears again. So, what this means is this is equal to this and this is equal to this. So, the left hand side of the last three equations are same, right, and what this then means, since UA is same, is my Ts minus T1 is equal to T1 minus T2 is equal to T2 minus T3, right. So, assuming that there is no sensible heat, the temperature drop which I get in the first effect, that the difference between temperature of steam and the liquid, is equal to the temperature drop I can get in the second effect, and is equal to temperature drop that I can get in the third effect. Let me call this some delta T. Now, let us say I compare that with a single effect evaporator, and I am using same amount of steam, right. So, for same amount of steam, for single effect, I am going to have S lambda S is equal to UA delta T, whatever we are having right here, the same thing will be there, right. But then for the same steam, I am now able to get a temperature drop which is basically 3 times in the triple effect case, because I got delta T drop in the first one, same drop in second one, same drop in third one. So, in a single effect case, the net drop is delta T, but for triple effect case, the net drop is 3 delta T, right. So, we can drive home a larger temperature drop along the three effects if I am doing this multiple effect operation, right, which can be good or bad, right, because what this means is that in order to operate the subsequent effect at much lower temperatures, I need to basically reduce the pressure in order to ensure that the boiling point remains at that lower temperature, right. So, let us say delta T is equal to 50 degrees Celsius, right. So, in third effect we are going to have, let us say, 100-degree or 150-degree lower temperature than compared to the first one, the feed on, right. So, therefore, we need to also ensure that the pressures are accordingly corrected, but that is what we get if I assume that the sensible heat is neglected. Now, let me also assume that the latent heat is the same, just for the sake of argument, and in that case I am going to have S lambda is equal to F minus L1 lambda and is equal to L1 minus L2 lambda. That is what we got from here, and that is also equal to L2 minus L3 lambda, right. So, for assuming that lambda s is equal to lambda 1 is equal to lambda 2 equal to lambda 3 is equal to lambda, it is not generally true. Latent heat will depend on temperature, but just for the sake of argument, just like we assume that the heat capacity is constant, let us also assume that the latent heat is also constant, just for the argument's sake, and then we will get this, right. So, now we can cancel this, and what we now note is we have F minus L1 is equal to L1 minus L2 is equal to L2 minus L3. So, the net change in the mass between the feed and the liquid coming out is the same in the three effects which I am getting, right. So, if I kind of try to solve this kind of an equation, I can note that my L1 is equal to something like S minus L1 is equal to something like F minus S, that is coming from the first two equations, right. And now L2 will be equal to L1 minus S, which will be F minus 2S, and L3 will be equal to L2 minus S if I use the first and last equation, and that will be equal to something like F minus 3S, right. So, correspondingly, if I want to find the vapors coming out, my V1 is going to be F minus L1, that is equal to S. My V2 is going to be L1 minus L2, that is going to be again equal to S, and my V3 is equal to L2 minus L3, which is equal to S. So, if I now look at the steam economy of this process, the steam economy is going to be the amount of vapor produced by the amount of fresh steam fed, which is going to be something like V1 plus V2 plus V3 divided by fresh steam fed is still S. So, this gives me 3S by S, which is equal to 3, right. So, this is for triple effect evaporator. On the other hand, if I had single effect, and if I still assume that lambda is equal to lambda in that case, my V will be equal to S still, but the steam economy is going to be something like V by S, that is equal to 1, right. So, provided that these assumptions are valid, the steam economy that is the kg of solvent evaporated per kg of steam fed, is 3 times in the case of triple effect evaporator. That is the natural advantage that we are getting. Clearly, in reality, it is going to be not such a drastic increase. It may be twice, it may be 1.5 times. The reason being that the latent heat will change with temperature, and we cannot make also the assumption of ignoring the sensible heat and those things. But it still brings the point home that whenever I am using the triple effect evaporator, what is also intuitively true, because I am using the vapor coming out as the heating media in subsequent effects, we can see that the steam economy for the multiple effect case will clearly be like at least something like theoretically 3 times in the triple effect case, or if you have n effects, then n times that what we get in the single effect evaporator. Of course, this is only the recurring cost. You will have a capital cost because you are putting in multiple evaporators. You will have an equipment capital cost that we also have to keep in mind, right? So it is not always maybe cheaper, because capital cost may be higher than the recurring cost in some cases. But in most cases, if you want to concentrate to high concentrations, it's a good idea to use multiple effects, because this will give you a better steam economy, right, than compared to a single effect. So let us now recap quickly with a few questions, quick questions. When will we choose reverse feed over forward feed for the multiple effect evaporator? I have discussed this. We will use it. We will use forward feed when we have a hot fluid. So therefore, the reverse feed is going to be preferred when we have cold feed. When we have cold feed, right, this is definitely the case. When we have cold feed, then since the feed is entering the colder effect, the reverse feed is better in that case, right? But it is also true that if you have viscous feed or viscous liquid, in that case the viscous liquid is leaving the hotter effect. As the concentration increases, liquid becomes more and more viscous. So in the case of reverse feed, it is leaving the hotter effect, and since the viscosity decreases with temperature, it will be easier to flow in the case of a reverse feed effect, right? The downside of this is the reverse feed will require pumping, and this will require no pumping. One other thing that may have come to your mind is why we have not used phase equilibrium relations, right? So whenever we had vapor liquid equilibria, in my I think second week of lectures, we have discussed about different fundamental laws and concepts in chemical engineering, and phase equilibrium was one of them, right? So why we are not using it, right? Indeed, if you think about it, you have two phases here. It may not look like this, but indeed there are two phases here inside the evaporator, a vapor phase and a liquid phase. And in principle, both may contain solute. Let me call the solute by some P, notation P, and let me call the solvent by some S. So both may contain the solute and the solvent, right? So therefore, if I assume some sort of phase equilibrium, I should have some sort of chemical potential equalities like mu P, that is for solute in the vapor, is equal to mu P of the solute in the liquid, and similarly for the solvent. So in reality, this is true, right? But we have assumed here for ease of calculations, and also kind of practically because the solute is assumed to be non-volatile, right? So we have assumed here that there is absolutely no solute in the vapor phase, right? That is the first assumption we have made. The second assumption that we have made is that whatever the boiling point of the liquid which is present here, this boiling point is unaffected by the presence of solute, right? So boiling point of solution is pretty much same as boiling point of solvent, right? So therefore, we simply used whatever data we had for the solvent to get the boiling point, and we assume that it is saturated. So therefore, we are avoiding the complications that we may have had from thermodynamics by doing that. But in reality, if you have to truly do it, you have to drop these two conditions, and you may have, even in very small amount of trace amounts, you may indeed have some solute in the vapor phase, and you of course have plenty of solute in the liquid phase, right? So from here you may indeed get some relation between the vapor phase mass fraction of the solute and, let's say, some k times liquid phase mass fraction of the solute, right? So in reality, something like this may come from the chemical potential equalities, and when we do separation processes, particularly distillation process, I will have these equations in there. But we are not using in the case of evaporators because we are assuming complete separation, 100% separation, and at least in this case, we are also ignoring the effect of boiling point elevation, which can, however, be accounted for by using, let's say, Duhring lines and enthalpy concentration charts, right? So that can still be taken care of. But the fact that we have not assumed any solute in the vapor, that is a serious assumption. That is only true if my solute is completely non-volatile, right? And that's not always true, but the amount that we get in vapor may be so small that that can be typically neglected, right? So as long as this is true, as long as we can get a near complete separation by evaporation, we do not have to worry about the phase equilibrium relations. So with that, I want to conclude the discussion of today's lecture. In the next lecture, we will take some examples on evaporators, and then in the following lecture, I will discuss about the numerical methods of solving whatever equations that we have derived so far. Thank you so much.